Dear students, in continuation of our discussions on units and measurement, today we will study about accuracy, precision of instruments and errors in measurement, as well as significant figures. All the points discussed in this chapter are important, and please open your book and note down. Accuracy, precision of instruments and errors in measurement. Accuracy. The accuracy of a measurement is a measure of how close the measured value is to the true value of the quantity. That is, if you buy a 1 kg of rice, that 1 kg is the true value of the rice. But the measurement could be less than 1 kg or more than 1 kg. Hence, the accuracy of this measurement is a measure of how close the measured value is to the value of the quantity. Precision. Precision is the degree of exactness. It tells us to what resolution or limit the quantity is measured. Precision is generally indicated by the precision of the instrument which we use for the measurement. Errors. The difference in true and measured value of a quantity is called the error of measurement. In general, errors in measurement can be broadly classified as a systematic error and random errors. A systematic errors are those which tend to be in one direction, either positive or negative. Some of the sources of systematic errors are instrument errors, imperfections in experimental technique or procedure, and personal errors. Random errors are those which occur irregularly, hence are random with respect to the sign or size of the size are called random errors. These errors occur due to unpredictable fluctuations in experimental conditions, personal errors, etc. Least count errors. As we know, many instruments have a limiting value called a least count. The errors associated with the resolution or the smallest limiting value of that instrument is the least count error. Let us take an example. Suppose the true value of a certain length is near 3.678 centimeter. Please note here, after the fraction point there are 3 digits, that is 3 is before dot and 678 is after the dot. The true value is 3.678 centimeter. In one experiment, using a measuring instrument of resolution 0.1 centimeter, the measured value is found to be 3.5. That means the resolution of this measuring instrument can be 3.5 or 3.6 or 3.6. Only one digit after the dot is observed. While in another experiment, using a measuring device of greater resolution, say 0.01, that is another instrument, we can measure up to 0.01 centimeter. Hence, the length is determined to be in that second instrument, it is 3.38. You see here, after the dot, there are 3.3 and 8. Two digits are there, centimeter. The first measurement has a more accuracy because it is very close. 3.5 is very close to 3.678, whereas 3.38 is far away. The difference is higher than the previous one. But less, the first measurement has more accuracy because it is closer to the true value, but less precision because it is only one digit after the dot, that is 0.1 centimeter. while the second instrument is less accurate but more precise. Thus, every measurement is approximate due to errors in measurement. Note: systematic errors can be minimized by improving experimental techniques, selecting the better instruments, and removing the personal bias as far as possible. For a given setup, these errors may be estimated to a certain extent, and the necessary corrections may be applied to the readings. Absolute error, relative error, and percentage error. Absolute error. The magnitude of the difference between the individual measurement and value and the true value of the quantity is called the absolute error of the measurement. It is denoted by mod of delta A. You know that error can be positive or negative, but when we take modulus or mod of delta A, the sign is ignored. Suppose the values obtained in several measurements are A1, A2, A3, etc., etc. up to AN. Then A mean is defined as equals A mean average equals A1 plus A2 plus A3, etc., etc., etc. up to A plus AN divided by N, where A1 and A2 are the values, measured values in different attempts, and N is the number of attempts or number of measurements. Let it be equation 1. Therefore, delta A1 is equal to A1, the reading of first attempt, minus A mean. Similarly, delta A2, absolute error delta A2 is equal to A2 minus A mean. And finally, delta AN will be equal to AN minus A mean. Mean absolute error. Therefore, mean of absolute error, previously in equation 1 we defined A mean, that is the error, absolute error, and A mean absolute error is mean of all the absolute errors. Therefore, delta A mean is equal to delta A1 plus delta A2 plus etc., etc., etc. up to delta AN divided by N. Instead of absolute error, we often use relative error or percentage error delta A. So let us define these absolute error, relative error and percentage error. Relative error, the ratio of mean absolute error to mean value of observation is called relative error. Here we take the ratio relative error as the ratio of delta A mean. Delta A mean is defined in equation 2 and A mean is defined in equation 1. So for each experiment we calculate A mean and delta A mean, and their ratio delta A mean divided by A mean is the relative error. Percentage error. Percentage representation of relative error is called percentage error, and it is given as percentage error del A is equal to del A mean. Del A mean is given in equation 2 divided by equation 1 into 100. Combination of errors. Error of a sum or difference. If we do an experiment involving several measurements, we must know how the errors in all the measurements combine. For example, we know density is equal to mass over volume. So there may be an error in density due to error in mass as well as error in volume measurement. Let us go into the details. Suppose two physical quantities A and B have measured values A plus or minus delta A and B plus or minus delta B respectively, where delta A and delta B are their absolute errors. To find the error delta Z in the sum Z is equal to A plus B or Z is equal to A minus B, we can write Z plus or minus delta Z equals A plus or minus delta A plus or minus of B plus or minus delta B. That is, using simple relations, Z is equal to A plus B or Z is equal to A minus B. So that becomes delta Z is equal to plus or minus delta Z is equal to delta A plus or minus delta AB, comparing left hand side and right hand side. Therefore, the rule is when two quantities are added or subtracted, the absolute error in the final result is the sum of the absolute errors in the individual quantities. So, individual quantities here, errors in individual quantities are delta plus or minus delta A plus or minus delta B. Oh, B, section B, error of a product or a quotient. Suppose Z is related by two quantities, Z is equal to A into B or Z is equal to A by B. So AB is product and A over B is quotient. Consider the relations. Let us take only Z is equal to AB. So Z plus or minus delta Z equals A plus or minus delta A plus B plus or into B plus or minus delta B. Sorry, I will read once again. Z plus or minus delta Z is equal to product of A plus or minus delta A into B plus or minus delta B. Therefore, multiplying, we get the right hand side is AB plus or minus B into delta A plus or minus AB plus or minus A into delta B. Neglecting, divide the left hand side by Z and right hand side by AB. We get 1 plus or minus delta Z by Z equals 1 plus or minus delta A by A plus or minus AB divided by B plus or minus delta A divided by A into delta B by B. Neglecting the product delta A into delta B as they are small, we get the maximum relative error as delta Z by Z is equal to delta A by A plus delta B by B. Therefore, we can also verify in the similar way that Z is equal to delta A by B. The rule will repeat. When two quantities are multiplied or divided, their error in the result is the sum of relative errors in the multipliers. So whether we divide or multiply, the errors are sum of their relative errors in the multipliers. Error of measured quantity raised to the power. So consider the relation Z is equal to A square. That is Z delta Z by Z is equal to, we applying this rule, sum rule, delta A by A plus delta A by A. That is equal to 2 times delta A by A. Thus, the relative error in A to the power of n, if the relationship Z is equal to A to the power of n is n times delta A by A. In general, if Z is equal to A to the power of P and B to the power of Q divided by C to the power of R, then delta Z by Z is equal to P into delta A by A plus Q into delta B by B plus R into delta C by C. Therefore, the rule is the relative error in a physical quantity raised to the power k is k times the relative error in the individual quantity. Let us solve some of the worked examples associated with absolute error, relative error, and percentage error. Example 1. Two clocks are being tested against a standard clock located in a national laboratory. At 12 hours 00 minutes and 00 second noon by the standard clock, the readings of the two clocks are given in the following table. So the readings are taken for 7 days, that is Monday to Sunday, and the clock number 1 readings are given in second column. Similarly, the readings are observed in a clock number 2 are given in the third column. If you are doing an experiment that requires precision time interval measurements, which of the two clocks will you prefer? So the question is, what is your preference between the two clocks? Let us solve it. Here first we have to understand the concepts. Concepts are two clocks are both the clocks, clock number 1 and clock number 2 are having errors which is varying on different days. So that has to be compared to the standard clock kept in national laboratory, and the standard time is readings are taken at 12 hours 00 minutes and 00 seconds. Let us solve it. The range of variation of over the 7 days of the observation is 162 seconds for clock 1. So the difference is the variation is calculated by knowing the difference between 12 noon and the readings of the clock 1. So clock 1 observations variation range variation is 162 seconds, and 31 seconds the range variation for clock number 2 is 31 seconds. That is, you calculate the difference here and find out, add and divide it by 7 days. The average reading of clock 1 is much closer to standard time than the average reading of clock number 2. See, this is very close to 12 o'clock, whereas this is 10. The important point is that a clock's zero error is not as significant for precision work as its variation, because a zero error can always be easily corrected. Hence, clock number 2 is preferred to clock number 1 because its variation is less. Next problem. We measure the period of oscillation of a simple pendulum in successive measurements. The readings turn out to be 2.63 seconds, 2.5 seconds, 2.42 seconds, 2.71 seconds, and 2.8 seconds. The question is, calculate the absolute errors, relative errors, and percentage errors. So, 5 readings are given of a simple pendulum, and readings are taken, and we have to calculate. It is directly simple calculation of absolute errors, relative errors, and percentage errors. So answer, the mean period of oscillation is given by t is equal to, you have to add all the readings, 2.63 plus 2.56, 2.42, 2.71 and 2.80 divided by 5, that is equal to, adding we get 13.12 divided by 5, that is equal to 2.624 seconds. That is equal to, taking the accuracy, all are accurate only for second digit after the fraction. So we have to take the reading as 2.62 seconds. So resolution is, so because it is the two digits are significant after dot, so 0.01 second. Hence errors in measurement are 2.63 minus first reading minus the mean period of oscillation, the average or mean of this one. So 2.63 minus 2.62 is equal to 0.01 seconds. Similarly, for second reading, which is 2.56 minus 2.62, that is equal to minus 0.06. So all the 5 readings we are calculating the errors in measurement by subtracting from the mean period of oscillations, that is 2.62. The respective reading, the mean period of oscillation is subtracted from the respective readings, measurements. So taking only the magnitudes, arithmetic meaning, so for absolute errors, arithmetic mean is delta mean is equal to, so we add all the differences, only neglecting ignoring the sign. We add and divide by 5, that is equal to 0.054 divided by 5, that is equal to 0.11 second. Therefore, period of oscillation is 2.62 plus or minus 0.11 second. Hence, a more correct way is to put 2.6 plus or minus 0.11 second. Therefore, the relative percentage error del A is 0.1. This is taken as 0.1 divided by 2.6 into 100, that is 4%. We will work some more examples of absolute error, relative error and percentage error. Example number 3. The temperatures of two bodies measured by a thermometer are T1 is equal to 20 degrees plus or minus 0.5 degrees and T2, the second body, is 50 degrees centigrade plus or minus 0.5 degrees centigrade. Calculate the temperature difference of the error. So errors are given, that is both the thermometers are having same errors plus or minus 0.5 degrees centigrade. But the question asked is only the difference, temperature difference. So since error is same, it gets subtracted. We have to find the temperature difference T2 minus T1. So let us do it. Answer. T dash is equal to T2 minus T1, that is 50 degrees centigrade plus or minus 0.5 minus 20 degrees centigrade plus or minus 0.5. So the difference is 30 degrees centigrade. That is the answer. Therefore, T dash is equal to 30 degrees plus or minus 1 degree centigrade. The error can get added plus 0.5 plus 0.5. It can see this can be 50.5 minus 20.5, or if you take the negative reading, it will be 49.5 and 19.5. So the T dash will be is equal to plus or minus 30 degrees centigrade plus or minus 1 degree centigrade. Example for the resistance R is equal to, given by the relations R is equal to V by I, where V, the voltage, is equal to 100 plus or minus 5 volts and I is equal to 10 plus or minus 0.2 amps. Find the percentage error. So the voltage error is plus or minus 5 volts and I current is zero point 0.2 amps. So we have to find the percentage error using the quotient formula. The percentage of error in V is 5% and I is 2%. Therefore, total error is 5% plus 2% equal to 7%. So please note here it is 0.2 amps for 10 amps, error is 0.2. For 100 amps, it will be 2%. Example 5. Find the relative error in Z if Z is equal to A to the power of 4, B to the power of 1 by 3 divided by C to the power of 1 and D to the power of 3 by 2. So the relative error in Z is given by delta Z by Z is equal to 4. 4 into delta A by A plus 1 by 3 into delta B by B plus 1 into delta C by C plus 3 by 2 into delta D by D. That is the answer. Example number 6. The period of oscillations of a simple pendulum T is given by the relations T is equal to 2 pi into square root of L by G, where T is the period of oscillation, L is the length and G is the gravitational force. The measured value of L is 20 centimeters, known to be 1 mm accurate, and time for 100 oscillations of pendulum is 90 seconds. Using a wrist watch of 1 second resolution, what is the accuracy of the determination of G? So we have to understand the concept. So accuracy of L is different from accuracy of G, and similarly accuracy of T is different. So we have to find the accuracy of determining G, calculating G, the gravitational force. Therefore, given T is equal to 2 pi into L by G. Therefore, G is equal to, simplifying, squaring, you say T square is equal to 4 pi square into L by G. And separating G on the left hand side, G is equal to 2 pi, that is 4 pi square L by T square. So this formula is rearranged as given here. And next we have to calculate the error using the formula, combinational errors. So G, delta G by G is equal to constant. So that is delta L by L plus, this is T square, 2 into delta T by T. Though it is in denominator, but the error adds up. It is a summation. Therefore, delta I by L is 1 mm. 1 mm is for 20 centimeter L, it is 0.1 divided by 20 plus 2 into, and 1 second resolution is 2 into 1 by 90, that is equal to 0.027. So error in G is 0.027. Thus the percentage error in G is 100 into delta G by G, that is equal to 100 into 0.1 divided by 20 plus 100 into 2 by 90. So we have to multiply each with 100. So in this equation, 2 into by 90, that is equal to 3%. Now we move on to the next section, that is 2.7, significant figures. The digits whose values are accurately known in a particular measurement are called its significant figures. Larger the number of significant figures, greater will be the accuracy in measurement. Rules for counting significant figures. All non-zero digits are significant. So all digits other than 0 are significant. All the zeros between two non-zero digits are significant. So if the 0 is there between the two significant digits, the 0 is very important. Leading zeros to the left of non-zero numbers are not significant. That is, the left the zeros on the left hand side are negligible or insignificant. Trailing zeros to the right of number without decimal point are not significant. Trailing zeros to the right of all the decimal point are not significant. That is, zeros after digits are decimal point are not significant. The powers of 10 are not taken as significant figure. For a number with a decimal, trailing zeros are significant. Example, let us take example. 2.308. This can be written as 0.002308 meters. Here it can be written as 23.08 millimeters or 23080 micrometers. These are the significant and insignificant digits after the dot. Rules for arithmetic operation with significant figures. In addition or subtraction, the final result should have as many decimal places as there in the number with least decimal places. So, in example 436.32 G plus 227.2 G gram plus 0.301 grams. This we can add and write it as 663.821. The final result should be rounded off to 663.8 because in the middle term we have only one digit after the dot, after the decimal point. After the decimal point there is only one digit, hence it should be the result 663.821 should be rounded off to 663.8. In multiplication oblique division, this final result should have as many significant figures as there in the original number with the least significant figures. Let us take some example. Density. Density we know mass over volume. So density is equal to 4.237 divide grams divided by 2.51 centimeter cube. So if you divide it, we will get 1.69 grams per centimeter cube. So the two significant digits are here in the denominator. So the final result should have as many significant as there in the original number with least significant figures. Least significant figures are in volume 2.51. So it should have two significant figures. Speed of light is given by 3.00 into 10 to the power of 8 meters per second. So 1 year will be equal to 3.156 into 10 to the power of 7 seconds. So 1 light year is equal to 9.47 into 10 to the power of 15 meters. So we have to mention like this 9.4, so 2 digits, 3 digits like this. If you say 1 year, it will be 3.156 into 10 to the power of 7 seconds. Rounding of uncertain digits. Preceding digit is raised by 1 if the insignificant digit to be dropped is greater than 5. So, and is left unchanged if the latter is less than 5. So, for example, 2.746 is rounded off. This 6 is greater than 5, so it is kept as 7. It becomes 5. It has to increase by 1, raised by 1. So when it is raised by 1, it becomes 2.75. And then 2.743. Now there is another number 2.743. 3 is less than 5, so we have to ignore it. So this becomes 2.74. This is the rounding off procedure. If the significant digit is 5 and the preceding digit is even, the insignificant digit is simply dropped, and if it is odd, the preceding digit is raised by 1. I will give another example. See, 2.745 is rounded off as 2.74 because it is the the digit here is 4, and if you are dropping 5, it should be left as it is. So even the insignificant digit is dropped. If in another case 2.735, because the preceding digit is even, so it has to be raised by 1. If you are dropping 5, this becomes 2.74. Speed of light is give another example, 2.9979245 into 10 to the power of 8 meters per second. That can be rounded off. You see here 8 becomes, this becomes 6 and this becomes 5. So this can be written as 2.3 into 10 to the power of 8 meters per second. Value of pi is 3.1415926. You may take the value as 3.142 or 3.14. We will take up some more worked examples of the section significant figures. Example number 7. Each side of a cube is measured to be 7.203 meters. So, cube is made up of length into breadth into height, and each side is 7.203 meters. What are the total surface area and the volume of the cube to appropriate significant figures? Let us solve it. Answer. Here, the number of significant figures in measured length is 4. So here it is 4. The calculated area and the volume should therefore be rounded off to 4 significant figures. Therefore, surface area of the cube is given by 6. There are 6 areas into of the cube, that is 4 sides, top and bottom. So it will be 6 into 7.203 whole square. That is area of each surface is 7.203 into 7.203. That is 6 into 7.203 meter square. So simplifying, we get 311.299254. Now we have to round it off to the 4 digits. Therefore, it becomes 311.29. Because the previous digit is even, it is made it as 7.113. Here 9 is there. If you delete 4, it remains 5. If you ignore 5, delete 5, it becomes 3. So it becomes 2.99299. So if you delete this, it becomes 3. So the surface area of cube is 311.3 meters square. Volume of the cube is given by each side is cube 7.203 whole cube meter cube. That is, if you multiply 7.203 into 7.203 into 7.203, we get the answer as 373.714754 meter cube. That is equal to 373.7 meter cube. Next example. 5.74 grams of a substance occupies 1.2 centimeter cube. Express its density by keeping the significant figures. Answer. there are three significant figures in the measured mass. So significant figures are 5, 7, 4. Whereas only two significants in the measured volume. So here measured volume has two significant figures. Express its density keeping the significant figures in view. Hence, the density should be expressed to only two significant figures. That is, two significant figures of volume. Therefore, density is equal to mass over volume 5.74 divided by 1.3. We will get the answer 4.8 grams per centimeter cube. This is the answer.